All right, we'll go ahead and start the recording for the digital people, and we're going to finally start forces today. I've been looking forward to this. I think that forces are really, really important to us. So these are the 10 topics that we're going to be trying to focus on whenever we do forces. So I think the first thing to try to go over is, well, when we talk about the word force, what are we talking about? Yeah, in ninth grade, we said that a force is a push or a pull. And we'll just say push or pull. We don't really have to go into a whole lot of detail on that one just quite yet. But what does that actually mean whenever we talk about like a force being a push or a pull? It makes something move. Okay, can you make something move without a force? Okay. Uh, yeah, but even if you so like knocking something off of a table, even if you knock something off of a table, you still had to exert a force on it to get it to move, right? Because you had to hit it, and when you hit it, you actually exerted a force on it, even though it was for a short amount of time. You have to exert a force on something to cause it to move. There is no circumstance where you can get motion to occur without a force causing it to push or pull. Okay? Do what? But what? Okay. All right. All right. So if you're on a hill like this, and you just let this go, right? Okay. So like you didn't actually push or pull it, right? You just let it go. That's what you're saying? Right. So like but you let it go. So what's the force here? Gravity. So like there is a force of gravity pulling down this way, and it makes it go down the ramp. So even though you didn't touch it, there is still a force acting on there. Okay. It's probably important to say a couple of things. The requirement for motion. So like motion. Actually, we'll go ahead and we'll get more specific. Change in motion requires a force. Okay. Change in motion requires a force. Because you can move at a constant speed, and if you're just on a frictionless surface, or if you're like floating out in space and you're just moving at a constant speed, there's no force acting on you at that moment. But if you want to change your speed, or if you want to change your motion, it requires a force to go along with it. That is important. That's worth noting. What was it? Yeah, there's all sorts of interesting things that happen in space. But fortunately, we don't have to worry about those too terribly much on AP Physics. A couple of other things about the forces is that there are two types of forces that we're going to talk about in this class. The first type of force is one called a contact force, and it's not rocket science. A contact force is one where you have to have direct touch. Okay, direct touch. And then the other type of force is a force that's called a field force. And a field force, not a force field, a field force is a force that doesn't have to have any kind of contact. It is a force that's applied through a field. So the couple of those things that is a field force is gravity is one, and magnetic force is technically a field force. So we can put magnetic force. North and South Pole, they don't have to be touching each other, but if they get close enough, they will interact with each other. And the other one that we're going to do in this class later on is the electric force, because the electric force is a field force, and you don't have to have direct contact in order to be able to feel a push or a pull from an electric force. Okay, we do get to play with the Van de Graaff generator, absolutely. That's one of the labs that we're going to do. So contact forces, anytime that we deal with contact forces, those are going to be like what we normally think of as like pushes or pulls. The field forces are going to be the ones where we actually have to like start thinking and analyzing what's actually happening, because it's pretty easy for you guys to get pushes and pulls straight down off the bat. Okay, so we know that a force is a push or pull. We know that it requires a change in motion for force to a force. A change in motion requires a force. And we also know the two different types of forces for AP Physics. I think that's all I really want to talk about for the first part. So let's do a rundown of Newton's first, second, and third law real quick, because I know that y'all did these pretty heavily in physical science. So I don't want to spend like a huge amount of time on them, but they are very important. So we'll be continuing moving down every single time. So Newton's first law And I'm going to go ahead and put second law and third law. We'll just put them all right by each other because they're all important. And we can talk about what they mean in words, but we'll have to analyze what they mean in math as we continue to go along. So, what does Newton's first law, Isaac Newton's first law of motion, tell us? Okay, for every action, there's an equal and opposite reaction is the third law. So, so the third law tells you that forces come in pairs. Okay, in pairs. Or if you want to write out for every action there is an equal and opposite reaction force, that will work as well too. But forces always come in pairs with each other. So if you were to take your hand and you were to push on the wall also pushes back on you. So at an equal amount. If the wall did not push back on you, you would Hulk smash through the wall because you would accelerate and you would accelerate through the wall. The only reason that you're not pushing through the wall is because the wall is pushing back on you. When you walk across the floor is pushing back up on you. If the floor was not pushing back up on you, you would Hulk smash through the floor. Okay? Like literally, because you would accelerate through the floor. So there has to be a pair, and forces like these always come in pairs. Okay? And that's Newton's third law. And we're going to talk more about that later. But um, I mean, we can if y'all want to. Like, because if every action has an equal and opposite reaction, how do we move? Exactly. So notice that whenever you said you push on the floor pushes on you. Those were two different objects, right? So the pairs don't have to be on the same object. Okay? Does that make sense? So if I push on the wall like this and the wall pushes back on me, okay? The forces are balanced out and I don't move. Okay. But if I'm trying to push across, like if I'm walking, I'm going to push down on the floor and then across this way, and the floor is going to push the opposite direction, and those forces are going to balance each other out. Okay. So these equal and opposite this way, but I go this way, and hopefully the floor is fixed and it doesn't go that way. Okay. If it was a carpet, yeah, if a frictionless environment, you just take one step and just like start sliding down the hallway. Shh. Yeah, that would be scary. Um, our brains cannot handle true frictionlessness because if it did, if this room was truly frictionless, if I stuck you in the middle of the room, you would not be able to get out because no matter what, you wouldn't be able to create a Newton's third law pair. So you would try to push, but there's no friction, so you wouldn't be able to push. Okay. First or second law? What do those say? Okay. Yeah, that's the first law. Okay, so um, it is the law of inertia. So I'm going to go ahead and I'm going to write out inertia because we are going to have to talk a little bit about inertia. And this is where we get like the object at rest stays at rest, stays, let's see here, object at rest, stays at rest. I can't spell. I can tell it's Friday. Okay. Object in motion stays in motion. So I'm just going to use ditto quotes. So object in motion uh, stays in motion unless disturbed by an outside force. This is what we're familiar with in ninth grade. By outside force. In AP Physics, I usually won't say those words. I will always try to address it as every mass has the property of inertia. Okay, so if an object has mass, then an object is going to have inertia that goes along with it. And that's your tendency to resist motion. The more mass we have, the more the more we're going to try to resist any motion that comes toward us. The bigger it is, the harder it is to accelerate. The smaller it is, the easier it is to accelerate. Second law. The second law tells you that the force exerted on an object is the product of the mass and the acceleration imparted on the object. So the second law is best written as F equals ma. And you've seen this in ninth grade. And what I'm going to do is I'm going to say that I don't necessarily like the way that this is written. So what I'm going to do instead is I'm going to say that the net or the net force is equal to the mass of the system times the acceleration. Okay, and I'm going to put an arrow there for the acceleration value. Okay, and there's one more thing that I'm going to have to add there too. Okay, so like if you're looking for the net force, you're going to have to add all of the different forces together. So I'm going to add one more little thing here. I'm going to put a Greek letter sigma. Okay, because we can't just use F equals ma anymore. It worked in ninth grade whenever you had one mass, but what if I gave you two different masses that were connected to each other? Well, they're going to be part of the same system. So what I'm going to have to do is I'm going to have to add these different forces together. Okay, so we're going to need to add these. So I'm going to add a summation to it as well. So F net is equal to the sum of the forces. Okay, I normally write, so like instead of writing just mass, I normally write mass of the system because those individuals, like sometimes we'll have things like broken apart from each other. Like, for example, if you have two objects and these two objects are tied together by a rope. Yeah, we're always going to assume in AP Physics that the ropes are magical, massless, frictionless ropes. So in AP Physics, don't worry about the ropes. But what I'm really trying to say is that if you've got two masses that are put together, and this is 2 kilograms and this is 2 kilograms, and they're tied, if they're tied together, if you pull one, it's going to pull the other. So the mass of the system is really 4 kilograms, not 2 kilograms. Okay. So you have to think about what your system is and what is actually moving. When we talk about a system is a summation of all of the different parts that add up to a whole. So if you're talking about a computer system is a bunch of different parts and it makes a computer. If you talk about a school system, the school system is all of the different schools that come together to make up the school. Okay? When we talk about a mass system, the mass system is all of the different masses that add together to make the whole. Okay, so if we're going to talk about something as a system, we're talking about the entirety of it. The difference is we can actually define the system, and we'll talk a little bit more about that later. Okay, but this is basically your first law, this is your second law, and this is your third law. Okay. Um, Next thing that I want to try to talk about when dealing with forces is I want to talk about the line of action. So I've kind of mentioned it before, and I'm going to mention it now, okay? And that's the line of action, and it's important. Line of action. This is the line of action is basically the direction of motion, and it's going to be important for us in our drawings to know what the direction of motion actually is. So if you are taking an object and you are pushing it across a floor, well, your line of action is going to be just straight across the floor. Okay, and the reason why this is important is because there are two cardinal directions that can occur here. There is the up and down direction, and there is the left and right direction. Okay, so we've got basically up, down, and then forward and backwards. And these are basically the directions that our forces can take. If we had some weird force that were occurring at a different direction, what we would want to do is we would want to break those down into components. We don't want to look at some like 45-degree northward force. That would be kind of weird. So if we had like a force diagram and somebody was like, I'm going to push this way, and like this happens, right? If you like, well, I mean, like, no, if you've got like a piece of luggage and you're pulling up this way, you're actually pulling up at like a 45-degree angle, right? Okay, so like, what about it in POE? I can't remember when we did forces, but it was a long time ago. That was like pre-COVID, so I was like, I don't know what happened. But yeah, oh yeah, we did talk about that. Now that it's like you just like made something click in my brain. Yeah. So this will be the direction of motion for something going left and right. But if you've got like a crane and you have a crane set up, yeah, I remember the trusses now. And you have a crane set up and there's a box attached to it. Well, the line of action for this crane is going to be like in the straight up and down direction. So your box, whenever it moves up, it's going to move up the crane or down the crane. Your box is not going to like magically, your box is not going to magically yeet over here and just be like, "Yo, boy, I'm over here now." If your crane does that, something is wrong. Okay, you're right, but we're just talking about like just this lifting up and down, right? So don't make this more complicated than it is. It's going to either go straight up or straight down. This is your direction of motion, up, down, or you could also have a left or right acting on it as well too. Okay? Circles are a different story. Circles, yeah, circles do count, but that's the next chapter. So, do you want me to go ahead and spoil it for you now, or do you want me to wait for the next chapter? Okay. So, like, if you're going around in a circle, you have what? No, 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 no. Now the deal is it's a really so like say you've got like an object and this object is tied to a string. It's probably the easiest way to describe the string and this thing is just moving this direction. It's going around in a circle. Okay? The line of action is the circle. Okay, so like if we were to try to draw the line of action is wanting to go in the circle. And where your balance points are is you have either going around the circle like this, clockwise, counterclockwise, up and down. Okay, so there's forces going this way and there's forces going that way. Okay, the force that points inward, the force that keeps you in the circle, is the centripetal force, not centrifugal. Okay, so the word that we're looking for here is centripetal force. So this guy right here, I'll show you. Centripetal. Okay, or as across the pond, they call it centripetal. Okay, so centripetal or centripetal, either way. If you want to sound like you're from across the pond, or if you want to sound like, uh, I don't know, Freedom Unit American, they say centripetal. It doesn't really matter to me, however you want to pronounce it, honestly. So that's the center-seeking force. That's the inward force. Centrifugal force is the effect of what happens because of the fact that you're going in a circle. So centrifugal force is actually called a fictitious force because technically you don't notice it. Like if you tried to, if the object, it's going to be really hard to describe right now without having to talk much about because like we're doing this like a chapter ahead, right? But if you're on a merry-go-round and you're on the merry-go-round, okay, you don't see the centrifugal force. You see a person just like randomly smashing up against the back of the thing. And you're like, whoa, that person's like being pushed this way. Okay. Right. So like you don't if you're on the rotating system, you don't necessarily see the centrifugal force. So it's a fictitious force, okay? And it depends on your frame of reference. If your frame of reference is rotating, it can be witnessed. If your frame of reference is not rotating, you don't see it. Okay, and I think I just said that backwards whenever I was talking about the merry-go-round. If your frame of reference is rotating, you can see the centrifugal force. Yeah, I did. I totally said it backwards. If your frame of reference is rotating, you can feel like you can see the people like being squished this direction, right? And you can feel that force. Okay, but if you're not on the rotating system, you're like, oh, this person is just being held in a circle. That circle has to like in order to be in the circle, it has to be pointing in towards the circle. But the people in there feel a push outwards, right? It's really just a Newton's third law pair. But if you're not part of the rotating system, you don't necessarily see it. Okay, that's the easiest way that I can try to describe it, and I will try harder when we get into the next chapter. Okay, so yeah, if we do a circle, the line of action like is the circle. If you are, and here's where it gets important. If we're dealing with like a pulley, and there's a mass on one side, and there's a mass on the other side, then the line of action like goes around the pulley. So the line of action is going to do this. It's going to go here, and then since this string is attached to the pulley, it's going to go around like this. Okay, so your line of action technically like wraps around the pulley, and that has some terrible things that go along with it because we said that this way is positive and this way is negative, right? Well, as you go around the pulley, that means that this direction is the positive direction and this direction is the negative direction. So if this thing goes positive, this thing on the other side also goes down, but that downward is the positive direction. Okay? Wherever the heavier mass is probably which side you want to make the positive and the negative because the heavier mass is going to pull down. Okay, so like if I put a 5 kilogram mass on the right side and a 2 kilogram mass on the left side, the 5 kilogram mass is going to pull it down and the two is going to go up. Okay, so since we said that down is always negative, you probably always want to put the heavy mass having the negative being down. Otherwise, you're going to do your problems backwards and still get the right answer, and there's nothing wrong with that. This is all on Earth, yeah. So and you can use g is equal to 9.8 meters per second squared. I cannot say like I can't guarantee you that they might not be like, oh hey, what's this going to be on some mystery planet? And we'll do a couple of problems like that where there is like a mystery planet and we have to find the acceleration due to gravity on it. We could totally do that. I think that's reasonable. Okay. There's going to be a lot of things that you're not going to like about this chapter. So if you're like, I don't like this, if you're like, that's okay. Sometimes we have to do things that we don't like because it makes us stronger. There we go. So if we're back to the ramp problem. So the line of action on something going down a ramp, the motion is going to go up and down the ramp. So the line of action isn't straight up and down. The line of action is actually like diagonally down this direction. Okay. And that means that we really only have like four directions. And we're going to kind of twist this around. So you can either go like this way or this way. And then there's going to be a couple of like this direction and this direction. These are all at 90 degrees to the line of action. Okay. Fortunately, if things are attached to ropes, they really don't go left or right. But in the case of a ramp, it does actually kind of move in two dimensions. So to make our life easier, we take our x and y axis and we just like align it to the line of action. So our x and y axis will be down the ramp instead of having to resolve like 80 million components as we go across. Okay, so we will use the concept of the line of action a lot. You're going to see me use it inside problems because I'm going to ask you, like, where's the line of action? Because if you're going to miss a problem, it's probably going to be because you added somewhere instead of subtracted somewhere. So something like really, really menial or really basic like that. It's not going to be because you're like, oh no, this problem is so incredibly hard. You're probably just going to miss up like a plus and a minus sign, to be honest. And that's the difference between getting the answer correct and getting the answer incorrect. Let's see here. There was one more thing that I wanted to talk about before we like started going crazy about this. We got the line of action. We've got Newton's first, second, and third law. Um, we talked about the mass of the system. Do what? We went over this over the next chapter, but I if you have questions like that, they need to be addressed before we get there because I mean it is relevant. So um, just because that it's in the next chapter doesn't mean that we don't get to talk about it because these things are all related to each other. You think what? I think everybody's brain kind of hurts a little bit in this case. Okay, so let's do like an easy like force problem. So there is a relationship between mass and acceleration. Mass and acceleration are um, multiplied together to equal the force. So if you take like, I don't know, we'll do some plug and chug. Those normally make y'all happy. So if we take a box and let's say that that box is 5 kilograms, okay, it doesn't make a whole lot of sense to talk about the acceleration because not everybody really has accelerometers just hanging around everywhere. So what normally happens, oh, I knew what we were going to talk about, and it'll come up here in just a second. Um, what normally happens is you end up using a force, and we use arrows to signify where the force is, and you can, yeah. So like a free body diagram will be taking this entire scenario and turning it into a dot. Now, if we're talking about the line of action, there is motion along this line of action, and let's say that this is a 10 Newton force, and I wanted to find the acceleration happening on it. This is a typical kind of physical science problem that you guys would see from in the past. So if you have like, okay, I know that the force is equal to the mass of the system times the acceleration. I have two of these things, and I just need to find the third one. Okay, saying mass of the system in this case is kind of redundant because there's only one object, but we should probably still include it. So the force is 10 newtons, the mass of the system is 5 kilograms, and the acceleration is going to be equal to, I don't know. So then this case it's just 10 divided by 5, and that comes out to be 10 divided by 5 is 2, right? 2 what? Meters per second squared? How do you know? Okay. Okay, so all right, well, here we go. Time for some dimensional analysis. F equals ma, right? Okay. Well, mass is in kilograms, right? And acceleration is in meters per second squared, right? Okay. So that means that anytime we're dealing with a force, 1 newton is equal to 1 kilogram meter per second squared. The the units of a newton is a kilogram meter per second squared. So if we have kilogram meters per second squared, so like if I said I have 10 kilogram meters per second squared, and I divided it by 5 kilograms, guess what? The kilograms go bye-bye, bye-bye, and I won't traumatize you with that again. So the acceleration is going to be equal to 10 divided by 5, which is 2 meters per second squared. Okay. So yes, if you divide a force by a mass, you're going to get an acceleration. Okay, because a kilogram meter per second squared divided by kilograms makes it cancel out. Okay. If you divide by acceleration, you're going to get a mass because you're going to be taking kilogram meters per second squared and you're going to be dividing by meters per second squared. They're going to end up canceling out. So yes, if you solve for these letters, this formula is dimensionally correct and this formula works. Okay. I just need to make sure that you guys actually were okay with that. Um, there are two other forces that are acting here as well. We're going to pretend that friction does not exist just because, and I think we'll just have to deal with that. Um, so there is a force of gravity which points down. You can call this one of two things. You can either call this F of G, like F with a little g right there, or you can call it mg, mass times acceleration due to gravity. Okay, please don't write out gravity all the way, but the two acceptable terms that I see on the AP Physics test is to write F sub g or mg. Those are fine. Okay, you don't actually have to solve it and write the number out. You can just say, hey, that's gravity. But is this thing Hulk smashing through the floor? No, so that means that there's another force pointing up this way, and that force, I better point it straight up. Sorry, that was slightly cattywampus. There we go. That's better. But there's an arrow pointing up this way that is in equal magnitude, equal length, and it's called the normal force, which we're going to call N. Capital N for the normal force, not lowercase n. Capital N for the normal force. Yeah, Newton's is also capital N, so sorry. If you want to, if that bothers you, write Fn for normal force. Okay, if that will make you feel better. Okay, Fn for normal force, Fg for gravity. In AP Physics, I normally write N, so if it makes y'all feel better to put F in, just remind me and I'll do that. but normally like if I'm just solving a problem by myself, I'll just write N for the normal force. So remind me. You can also put N with an arrow over it to show that it's actually a vector and not a unit. So there's a couple of ways that you can distinguish between normal force and newtons, and it doesn't matter. Just just don't get them confused with each other, and we'll be okay. Now, if we have the same situation, but instead of having a box, we have a box in a box. And this one is 5 kilograms, and this one is 2 kilograms. Okay? And I push on this box right here. What would the acceleration be in this case? And it's the same. Let's just say we push with 10 newtons. We're going to push 10 newtons across. Okay, so the mass of the system is 7 kilograms. So here's what we're doing. You're basically saying that this whole thing, you're saying that this whole thing right here is the system, right? Okay, so we're going to say that 10 newtons is equal to the mass of the system, 7 kilograms, times our acceleration. Okay? In that case, then what are we going to do? You just want to go 10 sevenths meters per second squared, right? Okay, whatever. I'll be fine with that. So you found that using the entire 5 kilogram block and the 2 kilogram block, that the acceleration on this entire system is 10 sevenths meters per second squared. And I can then, once you find that acceleration, you could then ask some more brain tricky questions that kind of make people think a little bit more. Okay. So like I want you guys to try to think about like the 5 kilogram block and the 2 kilogram block. What is making the 2 kilogram block move? Friction? Okay, so it has to be held on by friction, right? Okay, so friction is making it move. What's the force of friction on the 2 kilogram block? Is it 10 newtons? Yeah, can it be 10 newtons? What's the mass of the system in that case? Yeah. Okay, that's the mass of the 5 kilogram and the 2 kilogram block. But what if I asked, what is the force of the 5 kilogram block on the 2 kilogram block? Because you're not pushing the 2 kilogram block. Okay, which means that what's pushing the 2 kilogram block is the 5 kilogram block. So what we do is but we know that the object is accelerating. We know that it's accelerating at 10 sevenths meters per second squared, right? So what we can do is we're going to say, all right, well, in this case, the system is just going to be this guy. So I'm going to just focus in on this part right here. And I'm going to say this is part of my system. So I'm going to say, okay, well, I don't know what the force is, but I know that the mass is 2 kilograms. And I also know that the acceleration is 10 sevenths meters per second squared. So that means that my force is going to be 20 sevenths meters per second squared. Oops. How about we just call that newtons? Kilogram meters per second squared. Newtons. What's that come out to be? 2.26 newtons? 2.86. Okay, so it's pretty close to 3, right? Pretty close to 3. 2.86 newtons. Okay, so you can actually find that like this 5 kilogram block is actually pushing on this 2 kilogram block. Since we know the acceleration of both of them, then in order to keep that acceleration, it has to be pushing with a force of 2.86 newtons. So what I'm going to do is if you just write F, that's not really very specific, right? Because there's going to be a lot of forces going down here. So why don't we call that force of like 5 to 2? So we'll just write 5 to 2 for the 5 kilogram block to the 2 kilogram block. So I'll just write F of 5 to 2. That's the force of 5 on 2. Now, is the 2 kilogram block pushing back on the 5 kilogram block? With what force would it push back at? Gravity? Yeah, it is. There is definitely gravity pulling down on the 2 kilogram block for sure. Okay, and the gravity is pushing down on it, and it's like basically squeezing that 5 kilogram block on top of it. But it doesn't move. There's no vertical acceleration, so that's okay. But there is a force there, and that force is actually a part of the situation. Okay, the head tilt. Yeah, my head is tilting at what you're trying to explain to me. No, I don't think so. I don't think that's a good idea. Always try to communicate. Um, So basically, what I'm really trying to get is that there are a lot of force arrows that we could draw here. Okay, we have to be careful about what we set up our system to be because sometimes they play tricks on us and they try to ask for specific masses instead of the mass of the entire system. And when that happens, the very first thing that we need to do is we need to get the acceleration of the entire system first. When we find the acceleration of the entire system, then we can solve for individual pieces of the puzzle. Okay? That's what I'm trying to get at here. Because there are lots of forces acting on the 2 kilogram block. There's a normal force, there's a gravity force, there's a force on the 5 to 2 kilogram block, and there's also a force on the 2 kilogram block to the 5 kilogram block. Okay? But not all of them matter, right? Because a lot of them just end up canceling out. The 5 kilogram block has four forces acting on it, if we include friction, that which would be pulling it back. So there would be a force of gravity pointing down, a normal force going up, force of the 10 Newton block going this direction. I forgot about the force of the 2 kilogram block and the 5 kilogram block. So there's like tons of different arrows that we could draw here, and it's easy for it to get overwhelming quick, even with a simple situation like this. So, and you can only have arrows going in four directions unless you want to get fancy. And even in AP Physics, we don't get that fancy because their thought process is, can you think about it in terms of systems? That's really what we have to try to get down here is that conceptual understanding that the 5 kilogram block and the 2 kilogram block can act as a system together with each other. Okay? Does that kind of make sense? Okay. How much time do we have left? 10 minutes? Okay. Let's try a basic, let's do a bow and arrow. Let's try that. Uh-oh. Oh no. And then we immediately go to our 2019 notes, and I don't know how I just did that. 2020. Okay. Actually, yeah, let's go ahead and do it. I said we're gonna do it. Let's do it. It's not that bad. It's just another. I'm just trying to be nice to y'all, guys. I'm trying to be nice to you. I'm trying to be nice to you. It's Friday. You want me to be not nice? I can be not nice. This is a bow and arrow. It's really big. Okay. There we go. Yeah, it's a bow and arrow. Uh, Typical mass of a arrow. Typical force that you would pull back a bow. 20-pound force. Okay. So we're gonna pull back. We're gonna pull back 20 pounds. Whenever we let go, what's the force gonna be going this direction? About 20 pounds of force whenever you let go, right? Because whenever you pull this back, as long as it's standing still, if you're pulling back with about 20 pounds of force, which by the way, I think that's actually a larger number, but we won't go there. 18 grams, thank you, Google, right? And so that means that there's also going to be a force going this way of about 20 pounds of force. Now, pounds and AP Physics don't normally go so well together, so about how many newtons would 20 pounds be? 10.5 newtons? No, sir. No, sir. Okay, so like what you did is you just tried to go to kilograms. So like if you want to find the mass in kilograms, um, then you would divide. But I don't think that that's what we want to do. I think these are forces, so I think we want to try to go to newtons. How many newtons are in a pound? Google is your friend. Google is totally your friend. And whenever you guys work problems, if you see pounds, feel free to change them over to newtons. And feel free to use Google to do that. So 1 pound is about 4.4 newtons according to Google. That sounds about right. So 1 pound equals 4.4 newtons. So we'll write that up here. 1 pound equals 4.4 newtons. This is why people prefer to weigh themselves in pounds, because whenever they step on the scale and it says that they're like 875 newtons, they're like, ah, and they freak out because it makes them feel like they're a much larger number than what they are. So you definitely want to, if you're weighing, you want to use the pound scale. You don't want to use the Newton scale. So let's change these over. What's 20 times 4.4? About 80, 80 point, 80.80? No. 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 85? 85. 85. Okay. So 85 newtons. 80.8. 85 newtons. So if you got it, is it 88? Are we all okay? That 20 times 4.4 is 88. There you go. Because like zero point 0.4 times 10 is 4, right? So zero point 0.4 times 20 would be 8. So we got 88 newtons going back, 88 newtons going forward. And we said that the mass of an arrow is about 18 grams. Okay, so like we never want to use grams when we're dealing force calculations. We always want to use kilograms. So that's going to be divided by 1,000. So 14 grams. We need to move the decimal over 3 places. So that's going to be 0.014 kilograms. There's 1,000 grams. There's 1,000 grams in a kilogram. You got 14 thousandths. 14 thou. Okay, 14 thousandths of a kilogram. So 0.014 kilograms. Okay. So we're going to use this. We've got a force. We've got a kilogram. So that means we've got an acceleration. Okay. So let's find it. So force of the object is going to equal the mass of the system. Since there's only one force, I'm not going to put the sum times the acceleration. Okay. What's our force? 88. What's the mass of our arrow? 0.014 kilograms. Okay. Times the acceleration. We don't know the acceleration, right? Okay. Six what? 6,285 meters per second squared is equal to the acceleration, which means you would definitely not want to be that arrow during that time. Okay? So we have an acceleration now, right? You're ready, you're preparing to not like me. How fast is it going? Once it reaches the end of the bow. What's the average, like if you're just talking about like a human arm, because whenever you pull it back, it has to go back that distance. But how far you think you can pull it back? 28, 30 inches? Okay. How many meters would that be? 0.3 meters, about a third of a meter. That's reasonable. So why don't we do that? Oh, we're doing the math. Okay, it's happening. So we're just going to say that, like from here to when the arrow reaches the end. Because once it reaches the end, you're not going to have any control over that arrow anymore. It's just moving at a constant speed left and right. Gravity pulls it down, but, that's two-dimensional motion from last chapter. This distance between it, a third of a meter or 0.66? Which one do you want to use? How about we go half season, just do 0.5? Okay. We'll do half season, just do 0.5 meters. Seems like a lot. Seems like a stretch. That's a good pun. Stretch, get it? It's bow and arrow. Oh man, this is a tough audience. Fine. Fine. Be that way. We have a DVAT. What's D, VI, VF, AT? What's the distance? 0.5 meters of traveling through the bow. What's the VI? I don't know. Really? Really, you don't know? Oh, it's 0, right? Because right before you, like right whenever you let go of the bow, it's going to be going at 0 meters per second. Okay, what's the VF? That's what I'm looking for. Okay. The acceleration is not 9.8. The acceleration is 6,285 meters per second squared. That's big. Yeah, it's a bit. That's what? Correct. That is the rate of speeding up. Correct. So it's going to be a large acceleration, but it's going to be a large acceleration over a short time because it's going to go from 0 to the acceleration of 6,285 over a distance of zero point 0.5 meters. There is an equation that we can use here. We can either use any of our Vf squared equals Vi squared plus 2AD. Okay, that is one of the kinematic equations. Yeah, because the forbidden equation uses time, right? So yeah, so we can use Vf squared equals Vi squared plus 2AD. We have everything except for Vf, so yeah, the Vi is 0. We're going to do some classic plug and chug here. The Vf is equal to 2 times 6,285 times the distance of 0.5, and that's squared, so please take the square root of that whenever you're done. It is time for mathy plug and chug. Hopefully, if we can get it finished quick enough. 679.3, like this. Oh, okay, after you take the square root? It, so it's 79 point. Yes, the 2 and the 0.5 just cancel each other out. So it's just the square root of 6,285. So VF is equal to 79.3 meters per second, which is approximately about 140 miles per hour. Whew, I think we're done, right? I think I've hurt y'all enough for Friday. I never. Oh, okay. Then I need to try harder. I need to try harder.